7 April 1989. Norwegian Sea, 100 miles southwest of Bear Island. K-278 Komsomolets, Project 685, the Soviet Union's only titanium-hulled submarine, patrols at depth. At 1100 hours, Compartment 7 reports routine status. Within minutes, the control room receives a temperature alarm. The expectation is straightforward: compartmentation, suppression systems, and a reactor designed to shut down safely under casualty. The reality becomes something else. By 11:13, hydraulic pressure collapses. The vertical rudder jams. By 12:19, the captain abandons security protocol and transmits the submarine's name and position in the clear. By 16:42, the order is given: abandon ship. The rescue chain is already late. The water temperature, 2 degrees Celsius, will kill in 15 minutes. 69 men aboard. 42 will not survive. This is the documented record of how a prototype built for invincibility became a minute-by-minute fight against systems, smoke, flooding, and cold. The submarine, K-278 Komsomolets, was never meant to be a production boat. Built in Severodvinsk between 1978 and 1983, she was a single prototype, a test platform for technologies the Soviet Navy hoped would define the next generation of attack submarines. Her official designation was Project 685. Displacement, 5,800 metric tons submerged. Reactor plant, 1 pressurized water unit driving steam turbines. Weapons load, 6 torpedo tubes forward, capable of carrying nuclear-tipped weapons. The hull itself was the centerpiece. Titanium alloy, lighter and stronger than steel, built to withstand pressures at depths exceeding 1,000 meters. On 4 August 1984, during trials in the Norwegian Sea, Komsomolets reached a depth between 1,020 and 1,027 meters, an operational record that remains unmatched for combat submarines. The promise was simple: depth equals survivability. At extreme depth, an enemy torpedo or depth charge becomes less effective. Detection becomes harder. Escape from hostile forces becomes more plausible. But the design intent carried an implicit assumption that the greatest threat would come from outside the hull. The casualty that unfolded on 7 April 1989 would prove otherwise. The decisive vulnerabilities were not pressure-related. They were internal: cable routing, ventilation pathways, high-pressure air distribution, and the cascading loss of ship systems after reactor shutdown. Once fire began, compartmentation meant less than expected. Watertight doors could be shut, but cables and piping ran through penetrations. Smoke could arc through those pathways despite closed hatches. The boat's command structure was documented and hierarchical. Captain First Rank Yevgeny Vanin held overall command. Captain Third Rank Vyacheslav Yudin served as senior engineering watch officer. Lieutenant Igor Molchanov kept the deck log. Chief Engineer Valentin Babenko supervised the engineering plant. Lieutenant Leonid Zayats served as the ship's doctor, responsible for crew health and, when necessary, survival medicine. These men operated within a system built on procedure, training, and Soviet naval discipline. They expected to manage casualties according to doctrine. What they encountered instead was a failure mode that spread faster than doctrine anticipated. The reactor plant sat in Compartment 5, shielded and separated from the crew spaces forward and the turbine and steering machinery aft. The logic was straightforward: isolate the nuclear island, protect the crew, maintain multiple barriers. Shutdown capability was considered a safety cornerstone. Soviet reactors incorporated automatic protective systems designed to scram, insert control rods and halt fission under abnormal conditions. Once scrammed, the reactor would generate only decay heat, residual energy from radioactive decay of fission products. Cooling would continue via emergency systems. The assumption was that shutdown equaled safety. But shutdown also meant loss of propulsion. It meant loss of the primary electrical generation that powered ventilation, pumps, hydraulics, and communications. On a submerged submarine, power is not a convenience. It is the margin between controlled response and platform loss. Komsomolets carried emergency diesel generators for ship service power, but those systems required time to start, required personnel to reach them, and required breathable air to operate. The narrative that follows documents what happened when that margin disappeared. The submarine's layout was a linear stack of pressure-resistant compartments numbered from bow to stern. Compartment 1, torpedo room and forward berthing. Compartment 2, crew quarters and battery spaces. Compartment 3, command post, radio, sonar, and ship control. Compartment 4, crew accommodations and auxiliary machinery. Compartment 5, reactor compartment, heavily shielded. Compartment 6, turbine hall and main propulsion equipment. Compartment 7, auxiliary turbine, steering gear, and aft machinery. Each compartment could be sealed by a heavy watertight hatch. In theory, a casualty in one space could be isolated from the others. Soviet submarine doctrine treated compartmentation as a core survival principle. Close the hatches, activate suppression, restore ventilation, and continue the mission. The documented reality was more complex. Cables carrying electrical power, control signals, and sensor data had to run the length of the boat. High-pressure air lines fed ballast systems, fire suppression systems, and emergency breathing apparatus throughout the submarine. Ventilation ducts distributed breathable air and exhausted carbon dioxide. These systems could not stop at every bulkhead. They had to penetrate. Penetrations were sealed, with stuffing tubes, gaskets, and fire-resistant materials, but they remained physical pathways. A fire in one compartment could spread heat, smoke, and combustion gases through those routes even when hatches were shut. The concept of arcing through cableways appears in the incident documentation. It describes how fire propagated not by breaching a door, but by following the infrastructure that connected compartments. Once cables began to burn, their insulation released toxic fumes. Once ventilation ductwork heated, it transported smoke forward and aft. The boundary between compartments became porous. Hydraulics presented a related problem. The submarine's control surfaces, rudder and diving planes, required high-pressure oil to move. That oil was supplied by pumps driven by electrical motors. Loss of electrical power meant loss of hydraulic pressure. Loss of hydraulic pressure meant loss of control authority. At depth, a submarine without control surfaces cannot easily maintain a safe depth or heading. It becomes dependent on buoyancy alone, blowing ballast tanks to surface or flooding them to descend. This is crude, slow, and difficult to reverse. The control room watch could read instruments showing temperature, pressure, and system status, but those instruments depended on sensors, wiring, and ship's power. As the casualty developed, that information flow degraded. Vanin would later face critical decisions with what one account described as nearly complete lack of information. The engineered system that was supposed to provide situational awareness was itself becoming a casualty of the fire. The reactor shutdown decision would become the first major operational turning point. Soviet nuclear safety doctrine prioritized preventing reactor damage above almost all other considerations. A reactor breach could release fission products into the submarine, contaminating crew and spaces, and rendering the platform uninhabitable even if it survived the immediate casualty. The reactor officer's calculus was simple: turbines winding down, electrical systems failing, unknown damage in aft compartments. Better to shut down now than risk losing cooling or control. The decision was technically correct. It was also operationally devastating. Without reactor power, the submarine became a drifting shell. Every subsequent action, surfacing, damage control, communications, and ultimately survival, became harder. Soviet naval procedure governed every aspect of submarine communications. Messages were encoded, locations were masked. Even distress signals followed protocol: transmit in cipher, await authentication, coordinate response through the chain of command. The system assumed time to encode, time to decode, time to verify, time to task assets. It assumed that a submarine in distress would remain a functional platform long enough for that process to work. It assumed that rescue forces, surface ships, aircraft, specialized recovery units could be mobilized and dispatched within a window measured in hours, not minutes. The Northern Fleet maintained ready forces for submarine rescue, including aircraft equipped with radio direction finding gear, surface ships with medical facilities, and specialized diving teams. Norway, whose territorial waters and exclusive economic zone bordered the patrol areas, maintained its own maritime surveillance and rescue capability. Relations between the Soviet Union and Norway were complex, Cold War adversaries, but also neighbours with shared interests in search and rescue and environmental protection. Protocol existed for cooperation in life-threatening emergencies, but it required notification, coordination, and trust. The first distress signal from Komsomolets was sent in the early minutes of the casualty. It was garbled. The cause is not fully documented. Equipment damage, atmospheric conditions, or human error under stress. The result was delay. Northern Fleet Headquarters received indication of a problem but lacked clarity on severity, location, or required response. Minutes passed. More signals followed. At some point, the decision chain reached Fleet Admiral Vladimir Chernovin, Commander-in-Chief of the Soviet Navy. Chernovin's role was institutional. He could authorize cross-border coordination, task strategic assets, and override procedural delays. The documentation shows that Chernovin ordered all steps to rescue the crew, including potential assistance from Norway. But authorization is not the same as execution. Ships had to be identified, redirected, and dispatched. Aircraft had to be fueled, crewed, and launched. Norway had to be contacted through diplomatic channels or direct military-to-military communication. Each step consumed time. The critical constraint was not capability. The Soviet Navy had ships within 70 miles of the submarine's position. Norway operated maritime patrol aircraft and surface vessels in the region. The constraint was coordination and decision speed. A submarine on the surface in moderate seas is visible. It can be located by aircraft within minutes of reaching the search area. But locating is not the same as recovering. Aircraft can drop life rafts, survival pods, and emergency gear. They cannot winch dozens of men from the water. That requires surface ships with deck space, davits, nets, and medical facilities. In 36-degree Fahrenheit water, approximately 2 degrees Celsius, the human body loses heat faster than it can generate it. Muscle function degrades within minutes. Consciousness can be lost within 15 minutes. Death from hypothermia can occur within 30 minutes, even for physically fit individuals wearing some insulation. The timeline would prove unforgiving. The window between surfacing and rescue would become the fatal gap. The timeline begins at 1100 hours. Seaman Nodari Buchnikashvili was stationed in Compartment 7, the aftmost space aboard Komsomolets. His last report to the control room was routine. Minutes later, the control room watch observed a temperature rise in Compartment 7. The increase was rapid, too rapid for normal machinery warm-up or environmental change. Udin, the engineering watch officer, noted the alarm. Initial response followed procedure: attempt to contact the aft compartment, confirm status, assess the threat. Then the situation clarified. A high-pressure air line in Compartment 7 had ruptured. The exact cause remains undocumented in available sources, but the effect was immediate. High-pressure air, oxygen-rich, fed into a space where electrical equipment, cable insulation, and combustible materials were present. The result was not a slow smoulder, it was a flash fire, described in one account as like a blast furnace. Vanin and Babenko faced a decision within minutes. The submarine carried Freon-based fire suppression systems designed to extinguish flames by displacing oxygen. Activation was irreversible. Once released, Freon filled the compartment, smothering the fire, but also making the space unbreathable. The problem was human. Buchnikashvili was still inside Compartment 7. Attempts to reach him or confirm his status failed. The fire was spreading. Vanin, according to the documentation, reluctantly orders the system activated. The Freon discharged. Buchnikashvili became the first fatality. The suppression system worked as designed, but the fire was already beyond containment. The account explicitly states that despite activation and despite closed hatches, the fire arcs through cableways. Heat, smoke, and combustion gases found pathways forward. Compartment 6, the turbine hall, was next. By 11:13, cascading failures began. Turbine generators wound down. Protective systems engaged automatically as operating parameters drifted out of tolerance. The propeller shaft stopped. The reactor officer, fearing thermal imbalance or loss of cooling, made the decision: shut down the reactor. control rods inserted, fission halted. The reactor plant entered a safe shutdown state. The submarine, however, did not. Without steam to the turbines, electrical generation ceased. Emergency batteries provided limited power to critical instruments and lighting, but not enough to run pumps, ventilation, or hydraulics at normal capacity. At 11:13, precisely logged, oil pumps shut down. Hydraulic pressure dropped. The vertical rudder jammed in position. The stern diving planes could not be controlled. Komsomolets lost the ability to steer or maintain depth trim by normal means. The boat was still submerged, still taking on smoke, and now unable to navigate. Vanin faced a brutal calculus. Remaining at depth was not survivable. Ventilation was compromised. Smoke was spreading. Crew effectiveness was degrading. The only option was to surface immediately, by any means. He ordered main ballast tanks blown. Compressed air forced seawater out of the ballast tanks. Increasing buoyancy. The submarine began to rise. Without control surfaces, the ascent was uncontrolled. Vanin ordered additional ballast blown as the boat passed through 300 feet. The bow pitched upward. The submarine broke the surface stern low, her propeller and aft sections still submerged, her forward hull exposed to open air. It was 11:21. Surfacing solved one problem. Depth. It created others. The fire had not stopped. Aft compartments were now exposed to wind and waves, but the crew inside faced temperatures that would soon exceed 1,800 degrees Fahrenheit. The reactor was safe. The platform was dying. Surfacing did not mean breathable air. Smoke poured from hatches and vents. The fire in the aft compartments had spread through Compartment 7, Compartment 6, and into portions of Compartment 5 near the reactor boundary. External observers would later describe flames visible through openings and the rubber composite acoustic coating on the hull peeling away in strips, a visual indicator of sustained extreme heat. Inside the submarine, the atmosphere was toxic. Smoke contains particulates, combustion gases, and chemical byproducts from burning insulation, paint, rubber, and plastics. Among those gases, carbon monoxide, colorless, odorless, and lethal. Carbon monoxide binds to hemoglobin in blood far more effectively than oxygen does. Even low concentrations impair judgment and coordination. High concentrations cause unconsciousness within minutes and death shortly after. The submarine's emergency breathing system was designed for exactly this scenario. Crew members could don masks connected to a centralized air supply or self-contained units. The system allowed damage control parties to work in smoke-filled spaces while maintaining breathable air. Doctrine and training emphasized its use. As smoke thickened, personnel donned masks and continued their work. Then something unexpected happened. Men reported dizziness. Some became disoriented. Dr. Zayat suspected contamination. He tested the air supply. The result, documented in the incident account, was unambiguous. A fatal concentration of CO is detected. The emergency breathing system itself had been compromised. Smoke and combustion products had migrated into the air distribution network, likely through breaches in ductwork or via shared pathways affected by the fire. The system meant to protect the crew was now delivering poison. This discovery forced a grim recalculation. Damage control personnel could no longer rely on the breathing system. They would have to work in foul air, holding their breath or using improvised methods, accepting exposure to smoke and carbon monoxide. Effectiveness and endurance plummeted. Compartment access became a rescue problem. In Compartment 4, crew members had been cut off by smoke. Responders, now equipped with self-contained breathing gear independent of the ship's air supply, forced entry. 2. Officers were found alive, unconscious but recoverable. Compartment 5, the reactor space, was another target. Entry attempts succeeded in reaching some personnel, but the smoke and heat made prolonged work impossible. One man who entered Compartment 5 survived. Others did not. Parallel to the rescue attempts, another effort focused on restoring ship's power. The reactor was down and would remain down. There was no safe or rapid way to restart it under these conditions. But the submarine carried diesel generators for emergency electrical service. These generators could supply lighting, pumps, limited ventilation, and communications gear. Seaman Roman Filipov made his way to the diesel generator compartment and attempted to restart one of the units. He succeeded. Ship's power began flowing to essential systems. But Filipov became ill, likely from smoke or CO exposure, and could not remain at the controls. Captain 3rd Rank Anatoly Ispenkov took over, maintaining generator operation. The restoration of electrical power was a critical stabilization step. It allowed pumps to run, reducing flooding in some bilges. It restored communication between the control room and some forward spaces. It provided Vanin with degraded but functional instrumentation. Yet the larger picture remained dire. The fire aft was uncontrolled. The reactor was safe, but offline. Hydraulic systems were compromised. Ventilation was minimal. Carbon monoxide contaminated the breathing network. Personnel were divided, some in forward spaces fighting smoke and trying to maintain trim, others aft attempting damage control, still others topside where air was breathable but cold and wind-whipped. The submarine was on the surface, visible, but functionally disabled. The phrase, "dead in the water," would later appear in the documentation. It was clinically accurate. At 12:19, Captain Vanin made a decision that violated protocol, but acknowledged reality. He transmitted a distress message in the clear, unencrypted, plain text, containing the submarine's name, Komsomolets, and her position. This was not standard procedure. Submarine locations were classified. Even in distress, encoding was expected. But encoding required time, required functional communications equipment, and assumed that the receiving station could decode quickly. Vanin's decision reflected the gravity of the situation. The crew's survival now depended on speed, not secrecy. The message was received. Within minutes, the information reached Northern Fleet headquarters. Admiral Chernobyl was informed. He issued orders. Redirect all nearby vessels to the submarine's location. Launch rescue aircraft. Prepare to coordinate with Norwegian authorities if necessary. 3 Soviet surface ships were within 70 miles. They turned toward Komsomolets. The closest was several hours away at best speed. At 12:43, a rescue aircraft launched from a Northern Fleet airbase. The aircraft carried radio, equipment, visual observation capability, and air-droppable survival gear, rafts, pods, supplies, but no means to recover personnel directly from the water. Its mission was to locate, communicate, assess, and coordinate surface rescue. The flight time to the search area was estimated at roughly 90 minutes. Komsomolets, meanwhile, continued to fight internal battles. Smoke in the control room reduced visibility to inches in some areas. Ventilation was intermittent. Vanin worked to stabilize the boat's trim, the balance between bow and stern, using ballast and counterflooding. A port list developed. The submarine heeled to the left. Counterflooding corrected it. Then a starboard list appeared. Instrumentation was degraded. Vanin lacked precise data on flooding rates, tank levels, and structural integrity. At 14:20, the rescue aircraft established radio contact with Komsomolets. By 14:40, the aircraft broke through clouds and achieved visual contact. The account describes the submarine as dead in the water, with crew visible on deck. Sea state was moderate, not calm, but not storm conditions. The crew's morale reportedly lifted at the sight of the aircraft. Help had arrived. The assumption, understandable and human, was that rescue would follow quickly. The aircraft circled, confirmed the submarine's condition, and coordinated with fleet headquarters. It prepared to drop additional life rafts and a survival pod. But the aircraft could not affect rescue itself. Surface ships were still hours away. The critical decision, whether to don exposure suits, prepare for immersion, or remain aboard and attempt to save the ship, was influenced by the presence of the aircraft. Many crew members did not don wet suits. The water temperature was 36 degrees Fahrenheit. Survivability without immersion protection was measured in minutes. The next 2 hours became a slow-motion race between stabilization efforts and structural failure. Vanin ordered a small team, warrant officers and selected personnel, to remain below, attempting to manage flooding, maintain generator operation, and keep the boat afloat. Most of the crew moved topside or to forward spaces where air was better. Smoke continued to pour from aft hatches. The fire was still burning. At approximately 16:30, Vanin attempted to correct the starboard list by blowing port ballast tanks. The goal was to trim the submarine level, improving stability. The result was opposite. The account states that blowing the port ballast does not work and serves only to accelerate taking on water. The reason, documented in the analysis, was structural. The after ballast tanks were not equipped with Kingston valves, closures that could prevent seawater from entering through ballast tank openings when submerged, and the pressure hull had been breached by fire damage. Blowing the tanks expelled water, but seawater immediately re-entered through the breach and through uncontrolled openings. The effect was to increase flooding rate, not reduce it. The submarine began to settle aft. At 16:42, Vanin gave the order, "Abandon ship." The decision was irreversible. Once given, the effort shifted from saving the platform to saving lives. The account records that Vanin sent a final radio message shortly after the order, confirming abandonment and providing updated status. By 1700 hours, 2 large life rafts were inflated on the bow. The aircraft overhead prepared to drop additional rafts in a survival pod. The sea state, moderate earlier, was worsening. Waves made footing uncertain. Personnel climbed from hatches onto the casing, the external deck, and worked their way forward toward the rafts. The submarine's stern was lower in the water now, the bow tilted upward. The list made movement difficult. Crew members assisted each other, passing gear, helping injured or weakened personnel. Some men were already hypothermic from prolonged exposure to cold air and spray. The first raft launched successfully. Men climbed in, too many. The raft was designed for a specific capacity. That capacity was exceeded. The raft rode low in the water, waves washing over the sides. Dr. Zayats was among those in the raft. He gave instructions for survival. Stay low, huddle for warmth, keep hands and feet inside, hold on by any means. The second raft encountered immediate trouble. As it was being deployed, a wave overturned it. Men in the water struggled to right it or cling to it. A third raft went down with the submarine's initial sinking motion. Deployed too late, it broke free underwater and surfaced too far from the cluster of survivors to be reached easily. The aircraft dropped a survival pod and additional small rafts. Wind and sea state scattered them. Some landed near the crew, others drifted beyond reach. The reality was stark. Approximately 50 men were now in the water or clinging to overloaded rafts. Surface ships were still more than an hour away. The water temperature, documented at 36 degrees Fahrenheit, would kill in 15 minutes without insulation. Many men wore only standard shipboard clothing, insufficient for immersion. Hypothermia onset was rapid. The body's core temperature drops quickly in cold water. Initial responses, shivering, confusion, progressed to loss of motor control, inability to grip, and unconsciousness. Survivors later described hands going numb, inability to hold onto raft ropes and watching others slip beneath the surface. The large raft became a focal point. Overcrowded, men packed tightly, those on the outer edge partially submerged. Zayats continued to call out instructions. Do not fall asleep. Keep moving fingers and toes. Stay together. The aircraft circled overhead, relaying position updates to approaching ships, but the aircraft could only observe. The men in the water could see help, but could not reach it. At 17:08, Komsomolets began her final descent. The stern sank first, the bow rising higher. Crew still aboard, those who had remained below attempting to save the boat, faced a decision measured in seconds: evacuate immediately or go down with the submarine. 6 men were inside when the decision became impossible. As seawater poured over the conning tower, one option remained: the escape capsule. This device, unique to Komsomolets, was a spherical pressure-resistant chamber located near the base of the sail. Designed to separate from the sinking submarine and ascend to the surface, it was intended as a last resort survival system. The 6 men inside sealed the hatch. The capsule detached. It rose through the water column and broke the surface. But surface conditions, waves, wind, and the mechanics of opening the hatch under rough seas defeated the design. The hatch opened. Water flooded in. The capsule began to sink. Warrant Officer Slusarenko, according to the documentation, managed to escape. The others, including Captain Vanin, did not. The capsule sank with them inside. The first surface ship to reach the area was a Soviet fishing trawler, not a naval vessel. It arrived shortly after 1800 hours, approximately 1 hour and 20 minutes after the abandoned ship order, and nearly 1 hour after the submarine sank. Crew members from the trawler deployed nets and lines. They pulled survivors from the water and from the overcrowded rafts. The process was chaotic. Men were weak, hypothermic, some unconscious. Lifting them aboard required care. Rough handling could trigger cardiac arrest in severely hypothermic individuals. But speed was also essential. Every minute in the water reduced survival probability. The trawler's crew worked methodically, prioritizing those still responsive. Medical care aboard the trawler was limited. Blankets, shelter from wind, and basic first aid. The ship's galley provided hot liquids for those able to swallow. Some men recovered quickly once removed from the water. Others did not regain consciousness. The documentation provides casualty figures that evolved over hours. One account states that by the time rescue efforts began, 39 of the 69 crew members were already dead. The final toll, reported after all rescue operations concluded, was 42 dead. The causes of death varied. Some died in the initial fire, Buknikashvili in compartment 7, others attempting damage control in aft spaces. Some died from smoke inhalation or carbon monoxide poisoning. Some died in the capsule. The majority died from hypothermia after immersion. The interval between abandonment and surface rescue, the gap measured in minutes but felt as eternity, was the decisive variable. Aircraft provided surveillance and morale. Rafts provided temporary flotation, but neither prevented heat loss. The core temperature drop was inexorable. Surface ships arrived as fast as the physics of navigation allowed, but for many it was not fast enough. Soviet and Norwegian naval vessels arrived in the following hours. They continued search operations, recovering bodies and debris. The wreck site was marked. Initial surveys began within days, using naval assets to locate the submarine on the seabed. Depth soundings confirmed that Komsomolets had come to rest at approximately 1,670 meters, deeper than most salvage or recovery operations could reach with the technology available in 1989. The site coordinates were recorded: 73 degrees, 43 minutes, 16 seconds north, 13 degrees, 16 minutes, 52 seconds east. The location placed the wreck southwest of Bear Island, within the Norwegian Sea but in international waters. Norwegian authorities expressed immediate concern. The region was economically significant, fishing grounds, shipping lanes, and environmentally sensitive. A sunken nuclear submarine raised questions: reactor containment integrity, potential contamination, long-term monitoring obligations. In the era of glasnost, the incident could not be covered up. Soviet media reported the disaster within days. Major newspapers published accounts of the fire, the sinking, and the casualties. The narrative emphasized bravery and sacrifice, as was standard in Soviet military reporting, but it also acknowledged systemic questions. Western media picked up the story. The technical details, titanium hull, deep diving capability, nuclear torpedoes, drew analysis and speculation. The strategic implications were noted: loss of a unique prototype, loss of classified technology to the seabed, and potential environmental hazard from a reactor and weapons systems now beyond retrieval. Norwegian authorities formally requested information from the Soviet government regarding the submarine's radioactive inventory and the potential for contamination. The Soviet Navy responded with general assurances. The reactor had been shut down early in the casualty. Fuel remained contained within the reactor vessel. Depth provided isolation. These assurances were accurate in the immediate term, but incomplete for the long term. Radioactive materials decay over time, but some isotopes have half-lives measured in decades. Structural materials corrode, seals degrade. What was contained in 1989 might not remain contained in 2000 or 2020. The wreck of Komsomolets did not vanish from attention. Between 1989 and 1992, multiple survey expeditions were conducted using Soviet and later Russian naval assets. The research vessel, Academic Mstislav Keldysh, equipped with the Mir deep submergence vehicles, conducted detailed visual and photographic surveys. Igor D. Spassky, chief designer at the Rubin Design Bureau, the organization responsible for Komsomolets' design, led technical assessments. The surveys documented hull breaches, fire damage, and the condition of the reactor compartment and torpedo spaces. External coverings were observed. In the mid-1990s, a titanium sarcophagus was installed over portions of the torpedo compartment, intended to contain any release from the 2 nuclear torpedoes the submarine had been carrying. The reactor compartment itself showed visible damage, but no obvious large-scale breach. Instrumentation deployed near the wreck detected low levels of radioactivity in the surrounding seawater, slightly above background, but not at levels indicating major release. The Soviet Union collapsed in 1991. The Russian Federation inherited the wreck, the monitoring obligations, and the diplomatic relationships with Norway. Norwegian research institutions, particularly the Institute of Marine Research, initiated independent monitoring programs. Annual or biennial sampling campaigns collected seawater, sediment, and biological samples from the wreck area. The goal was to establish baseline conditions and detect any increase in contamination over time. The radioactive inventory aboard Komsomolets was known in general terms. The reactor core at the time of sinking contained fission products and transuranic elements. Total activity was estimated at approximately 29 petabecquerels, 29 times 10 to the 15th becquerels. A becquerel is 1 radioactive decay per second. A petabecquerel is 1 million billion decays per second. The number is large but abstract. To provide context, most of that activity came from short-lived isotopes that decayed rapidly in the first months and years after the accident. By the early 2000s, the dominant long-lived isotopes were cesium-137 and strontium-90, each with a half-life near 30 years. By 2019, 3 decades after the sinking, the remaining reactor activity was estimated at approximately 3 petabecquerels, almost entirely due to cesium-137 and strontium-90. The 2 nuclear torpedoes presented a separate concern. Each warhead contained fissile material, plutonium or highly enriched uranium, and conventional high explosives. The warheads were not designed to withstand seawater exposure indefinitely. Corrosion could breach containment. Plutonium, if released, would appear in seawater and sediment as specific isotopic signatures: plutonium-239, plutonium-240, distinct from reactor fission products. Norwegian and Russian authorities both emphasized that monitoring for weapon-grade material was part of the long-term assessment. Early surveys found no evidence of plutonium release. The titanium sarcophagus was intended to provide additional containment, buying time for corrosion to progress slowly rather than rapidly. But titanium, while strong and corrosion-resistant, is not eternal. Seawater at depth is cold, which slows some corrosion processes, but pressure and chemistry still act over decades. The narrative could have ended there: a wreck monitored, a hazard managed, a slow decay, measured in isotope half-lives and corrosion rates. But in July 2019, a Norwegian research expedition conducted the most detailed sampling campaign to date. Using a remotely operated vehicle equipped with manipulator arms and sampling bottles, the team targeted specific structures on the wreck. One target was a ventilation pipe opening, previously identified as a potential release pathway. The ROV positioned a sampling bottle at the opening. Water was drawn directly from inside or immediately adjacent to the pipe. The sample was recovered, sealed, and returned to the surface. Laboratory analysis followed. The analysis results were unambiguous. Cesium-137 activity concentrations in water sampled from the ventilation pipe range from below detection limits, less than 8 becquerels per litre, to 857 becquerels per litre. Background levels in the Norwegian Sea, far from the wreck, are approximately 0.001 becquerels per litre. The maximum sample represented an elevation of roughly 800,000 times background. Other samples from the same pipe during the same dive showed much lower or non-detectable levels. The conclusion: releases were occurring, but intermittently. The mechanism was likely related to pressure changes, water flow through corroded structures, or episodic breaches in internal containment barriers. The reactor compartment was not continuously venting radioactivity into the sea, but it was also not fully sealed. Leakage was real, measurable, and variable. Strontium-90 was also detected, though at lower concentrations than cesium-137. Both isotopes are beta emitters. They release electrons during decay, and both are biologically significant. Cesium behaves chemically like potassium and can be taken up by muscle tissue. Strontium behaves like calcium and deposits in bone. Neither is acutely toxic at low concentrations, but long-term exposure increases cancer risk. The key question for public health and environmental assessment was not the concentration at the source, but the dilution and transport pathways. Water sampled within centimeters of the vent pipe showed high activity. Water sampled meters away showed much lower activity. Water sampled hundreds of meters away returned to near background. The ocean is a massive dilution reservoir. Currents, mixing, and dispersion reduce concentrations rapidly. Biological uptake, by plankton, fish, or benthic organisms, concentrates isotopes slightly, but far less than in freshwater or shallow coastal systems. Norwegian authorities provided consumer context in their reporting. Fish samples collected from the region showed cesium-137 levels generally below 0.2 becquerels per kilogram, well below Norway's post-Chernobyl maximum permitted level of 600 becquerels per kilogram for food. The wreck site was deep, isolated from surface fishing activity, and far from commercial trawling grounds. The contamination was localized. The human dose pathway, seawater to fish to consumption, involved multiple dilution and decay steps. The assessed risk to Norwegian seafood consumers was negligible, but the finding was significant for another reason. It demonstrated that engineered containment, even in a robust titanium-hulled submarine, was not permanent. 30 years after sinking, the reactor compartment was still leaking. Plutonium isotopes were also analyzed. Samples showed trace detections of plutonium-239 and plutonium-240, isotopes consistent with weapons material. Concentrations were extremely low, near the detection limit of the instruments, but detectable. The presence of plutonium suggested that at least one of the nuclear torpedoes had experienced containment degradation. Whether this represented minor corrosion of the warhead casing or a more significant breach was unclear. The Norwegian reporting emphasized that no indication of any release of weapon-grade plutonium at hazardous levels had been observed, but also noted that isotopic signatures confirmed the warheads remained a potential source term requiring continued monitoring. The titanium sarcophagus was still in place, as observed during ROV surveys, but its effectiveness at preventing release versus merely slowing it could not be fully determined without destructive examination, which was not feasible or planned. The 2019 expedition report concluded with a measured assessment. The Komsomolets wreck remained a source of localized contamination. Releases appeared to be intermittent and variable in magnitude. Dilution in the open ocean reduced concentrations rapidly beyond the immediate vicinity of the wreck. Long-lived isotopes, cesium-137, strontium-90, would continue to decay, reducing source term strength over the coming decades. Monitoring should continue, both to track release trends and to provide early warning if structural changes or increased corrosion led to higher release rates. The wreck was described as a unique opportunity to study the long-term behavior of sunken nuclear materials in deep-sea environments. Other sunken submarines existed. Soviet, Russian, and American boats lost during the Cold War, but few were as accessible to scientific study or as well documented. The physical position of the wreck is fixed. 1,673 meters below the surface, the submarine rests on the seabed in near-total darkness. Pressure at that depth is approximately 167 atmospheres, 8 times greater than the pressure the titanium hull was designed to withstand when intact and operational. The hull, breached and compromised by fire, no longer resists pressure uniformly. Over 3 decades, seawater has penetrated compartments, accelerating corrosion of steel fittings, aluminum structures, and cable insulation. Titanium corrodes slowly in seawater, but it is not immune. The reactor pressure vessel, made of thick steel alloy, corrodes more predictably. Welds, seals, and penetrations are the weak points. The ventilation pipe identified as a release pathway is one of many structural interfaces between the reactor compartment's internal atmosphere, or what remains of it, and the external ocean. The 2019 ROV survey included high-resolution video and photographic documentation. The footage shows the submarine's sail, still upright, encrusted with marine growth. The hull is partially buried in sediment, a layer of fine silt and biological material that accumulates slowly at depth. The conning tower hatches are closed. The forward torpedo tubes are visible, some open to the sea. The titanium sarcophagus over the torpedo compartment is intact, though marine organisms have colonized its surface. The reactor compartment shows external damage, visible cracks, displaced plating, but remains structurally recognizable. The aft sections, where the fire originated, are the most heavily damaged. The stern is separated from the main hull, lying at a slight angle. Propeller blades are bent. The rudder and diving planes are frozen in their last positions. Inside the wreck, conditions are anoxic in most sealed spaces, low or zero dissolved oxygen. This slows some forms of biological degradation but does not prevent chemical corrosion. The reactor core, even shut down, contains residual radioactivity. Fission products and transuranic elements remain embedded in the fuel matrix. The fuel cladding, zirconium alloy tubes that contain the uranium fuel pellets, was designed to resist corrosion, but not indefinitely. Seawater ingress into the reactor vessel, if it has occurred, would begin slow dissolution of fuel materials. This process releases soluble isotopes, cesium, strontium, iodine, into the water. The measured cesium-137 concentrations in vent pipe samples are consistent with this mechanism. The releases are small, intermittent, and variable, suggesting that pathways open and close depending on sediment movement, structural shifts, or pressure-driven water flow through the damaged hull. The torpedoes are a parallel narrative. Each warhead is a sealed container, designed to be robust but not designed for decades of seawater immersion. The high explosives inside the warheads are chemically stable when dry, but can degrade when wet, producing acidic byproducts that accelerate corrosion of metal casings. The fissile core, plutonium or highly enriched uranium, is metallic and highly reactive with water. If the casing breaches, plutonium can oxidize and dissolve slowly, entering the seawater as ionic or particulate plutonium. The detections of plutonium-239 and plutonium-240 in the 2019 samples are consistent with minor breaches. The concentrations are low, parts per trillion in seawater, detectable only by highly sensitive radiochemical techniques. But they are measurable. They confirm that the warheads, like the reactor, are not fully contained. The Norwegian and Russian authorities agree on the core facts, but differ on emphasis. Russian official statements stress that the wreck poses no significant threat, that contamination is localized, and that the depth provides effective isolation. Norwegian statements agree that acute risks are absent, but emphasize the need for continued monitoring, the uncertainty in long-term corrosion rates, and the principle that any release of radioactive material into a shared ocean is a legitimate environmental concern. Both nations conduct periodic surveys. Both publish results in peer-reviewed scientific literature. The data are public, the methods are transparent, and the conclusions are cautious. The story of Komsomolets is not a secret. It is a documented case study in the intersection of military technology, maritime disaster, and long-duration environmental monitoring. The human toll is recorded in names. Seaman Nodari Buknikashvili, the first to die, killed by fire and freon in Compartment 7. Captain First Rank Yevgeny Vanin, who gave the final orders and died in the escape capsule. Warrant Officer Alexander Krasnobayev, also in the capsule. Captain Third Rank Vyacheslav Yudin, Engineering Watch Officer. Lieutenant Igor Molchanov, Deck Log Keeper. Chief Engineer Valentin Babenko. Captain Third Rank Anatoly Ispenkov, last seen operating the diesel generator. Seaman Roman Filipov, who restarted the generator but fell ill. Lieutenant Leonid Zayats, the doctor who identified carbon monoxide contamination and gave survival instructions on the raft. He survived the initial rescue, but reportedly died later from exposure-related complications. The list continues. 42 names, families notified, funerals held, medals awarded posthumously. The Soviet and Russian navies honored their sacrifice. Memorial services at Northern Fleet headquarters in Severomorsk included the unveiling of a bronze plaque. Similar memorials exist in Severodvinsk, where the submarine was built. The men are remembered as heroes, a designation that, in this case, aligns with documented actions. They fought a fire, managed a reactor casualty, attempted rescues in toxic atmospheres, maintained power under impossible conditions, and faced death in cold water. They did not fail. The systems failed them. The technical community drew different lessons. Submarine designers analyzed the compartment fire dynamics, the cable penetration vulnerabilities, and the hydraulic failure cascade. Changes were implemented in later classes, improved fire suppression systems, redesigned cable routing to limit fire propagation, enhanced emergency breathing systems with isolated air supplies, and better instrumentation for damage control. The escape capsule concept was retained in some designs, but modified to improve surface stability and hatch operation. The lesson was not that deep-diving submarines were unsafe. The lesson was that internal casualties required as much design attention as external threats. The reactor shutdown decision was reviewed. The consensus was that the reactor officer acted correctly. Preventing reactor damage was paramount, but the operational cost, loss of propulsion and ship's power, was acknowledged. Future designs would incorporate redundant emergency power systems, improved battery capacity, and faster diesel generator startup procedures. The environmental monitoring legacy is unique. Most Cold War submarine losses remain in deep water, unmonitored and largely forgotten by the public. Komsomolets became an exception because of its location, near Norway, in economically important waters, and because of the transparency forced by Glasnost and continued by the Russian Federation. The Norwegian Institute of Marine Research has conducted more than a dozen expeditions to the site since 1990. Each expedition produces a public report with data tables, isotope measurements, and risk assessments. The reports are dry, technical, and precise. They do not sensationalize. They do not exaggerate risk. They present evidence. Cesium-137 concentrations have varied over time, sometimes undetectable, sometimes elevated. Strontium-90 follows similar patterns. Plutonium remains at trace levels. The overall trend is slow decay, both radioactive decay reducing source strength and structural decay increasing release potential. The two processes work in opposition. Eventually, radioactive decay will dominate. In another 30 years, by 2050, cesium-137 and strontium-90 inventories will have decreased by another factor of 2. By 2100, residual activity will be a small fraction of the original, but that is assuming no major structural collapse or unexpected breach. Monitoring continues because the future is not guaranteed. The broader policy lesson is about recovery and salvage. Komsomolets was too deep to raise in 1989. Even with modern technology, recovery would be extraordinarily expensive and risky. The alternative, containment in place, monitoring, and manage risk, has become the de facto international standard for deep-ocean nuclear wrecks. The United States has at least 2 sunken nuclear submarines. USS Thresher, lost in 1963 at approximately 2,600 meters, and USS Scorpion, lost in 1968 at approximately 3,000 meters. Neither has been raised. Periodic surveys assess hull condition and radiation levels. The approach mirrors Komsomolets. Document, measure, report, and continue monitoring. The ocean floor has become an archive, not of intention, but of accidents and the slow arithmetic of decay. The final data point returns to measurement. July 7th through 10th, 2019. The Norwegian research vessel positions over the wreck coordinates. The ROV descends. Thrusters stabilize the vehicle against current. Manipulator arms extend. A sampling bottle opens, draws seawater, closes, and retracts. The ROV ascends. The sample reaches the surface in a sealed container labeled with date, time, depth, and location. It is stored cold during transit back to port. In the laboratory, the sample is processed. Gamma spectrometry identifies cesium-137. Beta counting measures strontium-90. Radiochemical separation isolates plutonium isotopes. Alpha spectrometry determines their activity. Numbers emerge. Cesium-137 at 857 becquerels per liter, the highest concentration measured in that campaign. Other samples from the same dive show lower or non-detectable levels. The conclusion is not panic. The conclusion is documentation. Releases are occurring, they are intermittent, they are measurable, they are localized. The Norwegian report provides context. 857 becquerels per litre sounds high. It is high relative to background, but it is not high relative to many industrial or medical sources. A typical nuclear medicine dose for a patient might involve injection of tens of millions of becquerels. A nuclear power plant's routine liquid effluent discharge might be measured in billions of becquerels per year, but diluted to low concentrations before environmental release. The Komsomolets release is uncontrolled, but it is also microscopic in volume. The ventilation pipe opening is perhaps 10 centimeters in diameter. Water flow through it is episodic. The total release rate, integrated over time, is estimated in the report at kilobecquerels to megabecquerels per year, far below the radioactivity released annually by a single operating nuclear power reactor's permitted discharges. The significance is qualitative, not quantitative. It proves that containment is imperfect. It justifies continued monitoring. It does not indicate imminent hazard. The human dimension remains. 27 men survived the sinking. They returned to families, to the Northern Fleet, to civilian life. Some continued naval careers, some retired, some struggled with trauma. Dr. Leonid Zayats, whose identification of carbon monoxide contamination likely saved lives, became a symbol of competence under pressure. His survival instructions on the overcrowded raft were cited in later training materials. The engineer who restarted the diesel generator, Filipov, and the officer who took over generator operations, Ispenkov, were recognized for actions that gave the crew additional time. The warrant officer who escaped the capsule, Slyusarenko, carried survivor's guilt, as many do. He was the last man off the submarine, and the only one from the capsule to live. Interviews conducted years later describe his reluctance to discuss the event, his sense that he had done nothing special, and his insistence that the real heroes were the 42 who did not come home. The submarine herself, Project 685, K278, Komsomolets, remains on the seabed. She is a navigation hazard, marked on charts. She is an environmental monitoring site, visited by ROVs. She is a war grave, resting place of sailors. She is a data source, contributing to understanding of long-term radioactive behavior in deep-sea environments. She is a case study in submarine design, fire dynamics, rescue logistics, and international cooperation. She is all of these simultaneously. The story does not have a tidy ending. The wreck does not disappear. The radioactivity does not vanish. The monitoring does not stop. But the story does have a conclusion. The documented record is complete enough to learn from. 35 years after 7th April 1989, the lessons remain relevant. Submarines still patrol. Reactors still operate. Fires still occur. Rescue chains still depend on timing. Cold water still kills. The technical details of Komsomolets, titanium hulls, deep diving capability, freon suppression, escape capsules are specific to one boat, one era, one design philosophy. But the underlying dynamic is universal. Complex systems fail in complex ways. Resilience comes not from single barriers but from layers, physical, procedural, human. When one layer fails, others must hold. On 7 April 1989, several layers failed in sequence. Some held. The reactor shut down safely. Personnel fought the fire. Communication reached the outside world. Rescue assets were dispatched. Survivors were recovered. The outcome was tragic, but not total. Knowledge survived. Memory survived. And the wreck, 1,673 meters below the Norwegian Sea, continues to teach, quietly, measurably, and without exaggeration.